Have you ever wondered where beaches come from? Why some beaches are sand and others are rock? What happens to sand carried downstream by rivers? Why do beaches change from season to season and year to year? Keep watching. The answers to these and other questions are just ahead. The Beach, a Waterfall of Sand, by Sean Chamberlain. Beaches. We think of them as a place to relax, watch the waves, contemplate new horizons. But where do beaches come from? To understand beaches, we need to know a little geology. Meet the sediment family. Beaches are primarily composed of sediments, solid particles of various sizes fragmented from rocks. We classify sediments according to their size, the diameter of their individual pieces, that is, their grains. The largest grains are boulders. The smallest grains are clay. While all sizes of sediments may be found on a beach, sand grains are the most common. Big rocks fragment into smaller rocks, which break down into even smaller rocks, and so on. The rock from which sediments originate is often referred to as the parent rock. All sediments are children of parent rocks. Sediments are created through the process of weathering, the alteration of rocks by the environment. Physical weathering involves the pounding and smashing of rocks by earthquakes and landslides. Or the breaking apart of rocks as water freezes and expands in cracks, a process called ice wedging. Chemical weathering generally occurs as water made slightly acidic by carbon dioxide dissolves the soluble parts of rocks. Ever seen melted statues? Biological weathering happens when organisms break apart or dissolve rocks. Tree roots fracturing rocks are a familiar example. Weathering of rocks is all around you. It's responsible for making sediments. Now that we know what sediments are and how they form, you might be wondering, how do they get from the mountains to the beach? The answer lies with water, winds, and earth movements. Water lifts sediments up and carries them downstream. Sediments exhibit three types of movement in flowing water. They may be suspended in water, literally floating in the stream of water as it heads downhill. They may hop along the river bed, a process called saltation, or they may be rolled or dragged along the bottom. Naturally, larger sediments need more force to move than smaller ones. Put another way, smaller sediments like sand, silt, and clay are easily suspended and carried downstream. As a result, larger sediments tend to stick closer to their point of origin. Smaller sediments may travel for hundreds and even thousands of miles under the right circumstances. Winds carry sediments, too. Winds are important in the formation of coastal sand dunes. They also carry sand from the Sahara Desert all the way to the Americas. Earthquakes and gravity can produce land movements that transport sediments downhill. The actions of water and wind have another effect on sediments. Because small sediments move more quickly in a given flow, and large sediments move more slowly, the faster particles speed away from their slower counterparts. The end result is sorting, the separation of different sized sediments due to flows of water or wind. Larger sediments like boulders and cobbles tend to remain upstream. Smaller sediments like silts and clays move far downstream. Pebbles and sand fall somewhere in between. The downstream transport of sediments by rivers raises one critical question: why don't sediments pile up at the mouths of rivers? The answer lies in waves. Waves pick up where rivers leave off. Waves move sediments down the beach. Perhaps you've experienced this current along the shore. Ever go out swimming only to find yourself a good distance from where you entered? That's because waves striking the beach at an angle generate a current of water along the beach. This current is called the longshore current. The movement of sediments by the longshore current is called longshore transport. Waves also move sediments back and forth along the beach face. The back and forth motion of sediments up and down the beach face is called cross-shore transport. Both longshore and cross-shore transport are important in supplying sand to and removing sand from a beach. First, breaking waves exert force on the seafloor and lift its sediments. High-energy waves, the big ones, drag more sand backward than forward. They carve out beaches. Low-energy waves, the smaller ones, push more sand forward than backward. They build up sand on the beach face. If waves approach at an angle, they create a longshore current. The longshore current moves sediments along the beach, opposite the direction of incoming waves. Waves drive the movement of sediments along the beach, which is why the shoreline changes every time you visit. The final destination in our sediments travels is not an obvious one. To observe what happens to sediments where beaches end, we must look beneath the surface. Behold the submarine canyon. Like the canyons you see driving along a mountain road, submarine canyons stretch across the seafloor. They drain sediments from beaches and channel them downhill into deeper waters. Off the coast of Southern California, 4 major submarine canyons play a role in the transport of sand away from beaches. The Mugo Canyon off Malibu, the Redondo Canyon which abuts Redondo Beach, the Newport Canyon right off the Newport Inlet, and the La Jolla Canyon near the Scripps Pier. Submarine canyons represent the third and final stage of a sediment's journey. Together with rivers and beaches, they form what is known as a coastal cell, the pathway of sediment transport from mountains to the sea. 4 major coastal cells encompass the beaches of Southern California: the Santa Barbara Cell, the Santa Monica Cell, the San Pedro Cell, and the Oceanside Cell. Together, these systems create a dramatic waterfall of sand, making Southern California's beaches among the most prized destinations in the world.